Good afternoon, ladies and gentlemen. We represent AgriSmart Engineering, the most innovative tech company you've probably never heard of. Luckily, that changes today. Let me introduce the A team. My name is Beckerling, and I'm a chemical engineer. I'm living the dream because I've co-founded an agri-tech company with my best friend, Anlu van Wyk, who is a mechatronic engineer. What we do is we develop technologies which facilitates controlled environment agriculture. This includes LED lighting, recirculating hydroponic systems, and data management and automation systems. We combine these offerings for turnkey facility designs and implementations, which are essentially infrastructure projects. Our vision is to unlock the full potential of controlled environment agriculture across the African continent. Before I dive in, I just want to give you guys some background. When we founded the company in 2020, there were 15 licensed producers. As of today, we have 103 licensed producers in South Africa. And on the right-hand side, you'll see a graph showing the breakdown of licenses per province, with the graph or the map on the left-hand side showing the province with the respective number of licensed producers in that region. Right, so the topic today is the technology selection framework. What is this exactly? Essentially, it is a snapshot of your production efficiency. It is a very deliberate curation. And make no mistake, it underpins the prospects of your commercial success. The goal of my presentation today is to bridge the gap between the engineering required to facilitate the optimization of the cultivation process and the rands and cents, euros and cents, or whatever your currency is, and cents of cannabis cultivation. So without further ado, let's make some sense. Essentially, your technology selection framework can be broken down into the following constituents: environmental control, irrigation, control, and of course, lighting. I'm about to introduce a concept you are all probably familiar with, and that guides the framework for your optimization problem in this industry. Photosynthesis. Building with light. That's literally what it means. Light is the catalyst for photosynthesis. So what exactly is light? Light is electromagnetic radiation. It is a transverse wave where the oscillation is perpendicular to the advance of the wave. You've all probably heard the concept, the particle duality of light. And that essentially means that light particles are waves at the same time. They have characteristic wavelengths, which translates to a characteristic amount of energy associated with those wavelengths. These are called photons. Now, there's a vast spectrum of electromagnetic radiation, and only some of it is useful for photosynthesis. This is called PAR radiation, or photosynthetic active radiation. You can see the visible spectrum here at the bottom, which nearly correlates with PAR radiation, which in traditional literature was defined as 400 to 700 nanometers, but modern definitions have included wavelengths before and after that mark. Let's get into it. What is PPFD and what is DLI? Well, these are the two most important metrics when it comes to building with light. The first refers to the photosynthetic photon flux density. Now, what is a flux? A flux is a measurement of intensity over area per unit time. So you will see this PPFD. Imagine I was carrying a bucket and I'm trying to catch these light particles as they're falling from the sky. And essentially the amount of particles I catch correlates to my instantaneous flux or light intensity. The DLI is the summation of the light intensity over the day length of that specific photo period. Right, building with light, a two-step system. On the right-hand side, we've got an organelle called a chloroplast. These are in every single plant cell. You will see that you've got these little sac-like structures called thylakoids, and a stack of these little pancakes is called a granum. This is where the magic happens. We've got two types of reactions which happen in parallel and all the time, and they drive this process. The first is the light-dependent reaction, and the second, the light-independent or the Calvin cycle. So what I'm going to do next is unpack the constituents of each of these processes and link them to the relevant engineering considerations when it comes to designing and implementing a successful commercial project. Let's start with the light harvesting mechanism. How does it work? Well, essentially, inside of these thylakoid membranes, we have got things called reaction center complexes and photosystems. You'll see photosystem 1 and photosystem 2. Don't worry if it seems counterintuitive. This is just the order in which they were discovered by science. How it works is when a photon strikes these membranes, you get a phenomenon called electron excitation, which essentially means that there is an excited state, and that electron bounces around like a pinball, and it strikes all of the other molecules until eventually it reaches the reaction center complex, where it is accepted by the primary electron acceptor. We've got different types of phytopigments. And these phytopigments are what allows the plant to absorb certain wavelengths of electromagnetic radiation. So you'll see here on the left-hand side, we've got a graph which shows the wavelength of light, and on the corresponding y-axis, you see the molecule which facilitates the absorption of wavelengths of that phytopigment. So, how does it work? How does light energy translate to commercial success? What does the science say? On the right-hand side, you have your ppfd on the x-axis and your selective leaf weight on the y-axis. And on the left-hand side, your ppfd on the x-axis and your inflorescent dry yield on the y-axis. These two graphs correspond to your vegetative and inflorescent or flowering cycles, respectively. We can see from the data that there is a near linear increase in each metric for performance as you increase light intensity. This is quite obvious. But does that mean you can just spam light and reap the rewards? Of course not. We've all heard of too much of a good thing, and that is most certainly true. Giving energy comes at a cost, a capital expenditure, and an associated operational expenditure. You will see here on the right-hand side of the graph that we start reaching a point where the slope approaches zero, and that is exactly where we start seeing these diminishing returns. You do not want to be in an instance where the capex and opex to move you along the graph exceeds that point of diminishing returns, because then you are past the point of commercial viability. That is not money well spent. Of course, you can also increase the amount of light that the plants uptake by increasing the limiting reagent in this process, carbon. So the net rate of carbon exchange will increase with the light intensity after light inhibition. But again, that comes at a capex and at an opex. So you need to be sure to walk this line diligently. Now, how does that link to your environment? Well, these little beans are actually drawings of stomata, which essentially allow respiration and gas exchange. On the right-hand side, we've got nice turgid, swollen guard cells and a nice open pore. This facilitates evapotranspiration and carbon fixation. So gas exchange can happen and photosynthesis is happening properly. On the left-hand side, you'll see the guard cells are shrunken. They are closed. So there's no room for gas exchange, and photosynthesis is halted. Why does this matter? Well, if you look at your Calvin cycle, at that stage 1, it's all about the carbon fixation. Plants are mostly carbon, and they need to fix this carbon to physically build themselves. So if you do not allow for nice open pores, you will have stagnant photosynthetic rates. How does this link to your environment? Well, it's all about turning the dial. Imagine a valve that you open or close, and how that works, the mechanism, is called the vapor pressure deficit. Essentially, a transpiration gradient. A vapor pressure deficit is essentially a combination of surface leaf temperatures, ambient temperatures, and humidities. And you can see that there is no silver bullet. There is a wide range of specific combinations which facilitate sufficient vapor pressure deficits for accelerated rates of photosynthesis. If you are in the red, your guard cells are closed. If you are in the red, your guard cells are closed. So as you step up this growth process, you want to step up that vapor pressure deficit, and you can see we start in the green zone for propagation and early veg, and we move over through mid and late flower. This is essentially what your HVAC is all about, because your heating, ventilation, and air conditioning is what determines where you are on this matrix. So what ties it all together? It's energy. Cooling load is the golden thread. It's the amount of energy needed to remove from an environment to maintain your temperature in an acceptable range. Of course, you want to keep it in a range which maximizes your photosynthetic processes. There are many different contributions or contributors to your cooling loads. Quite briefly, these are the size of your grow area. Of course, your lighting, because you can't talk about lighting without talking about cooling. We are talking about your electromechanical loads, which include mechanical aeration and irrigation. You are talking about occupancy, the people who actually tend to those rooms and who work with your product. And then you are talking about carbon generation, whether you burn hydrocarbons and release CO2 with energy, which needs to be dealt with, as well as extra water, or whether or not you're doing a canistered CO2, which doesn't add those but is less efficient. All of these need to be considered, and the right approach needs to be followed. There's a strong interdependence of cooling load. So this is called a Venn diagram. These circles represent some of the largest contributors to your cooling loads, and the intersection represents the area in which they feature. So for example, light and irrigation has got to do with humidification because it drives what? Evapotranspiration. Okay? Light and electromechanical loads generate heat, so what do you need to do? Heating, ventilation, and air conditioning. I'm not going to go through the entire matrix, but the point is that there's a very strong interdependence between the constituents and contributing factors which make up your cooling loads. And as you will see, this translates to the capex you spill, spending money to build the infrastructure, and the running costs associated with your plant. This is based on a case study for a 400 to 500 kilogram per annum facility indoor. And you can see on the right-hand side, we've got the facility power consumption fraction by the section. Mainly GACP cultivation, good manufacturing practices, good storage practices, and your general area. You want the blue slice of the cake to be as large as possible, because that means your costs are mostly in the sector of the facility, which is going to promote your revenue and actually give you a return. When we look at that 86% and we break it down, we gain some very interesting insights. The cultivation power consumption broken down reflects the following. You can see the yellow bar, 44 plus 12 plus 34. That is 90% of your energy spent in cultivation is spread over lighting, HVAC, and mechanical aeration. That is a significant amount and an invaluable business optimization insight. When you look at the influence of cooling loads as a function of lighting, you'll see the following. If we look in the first column, we've got the section of the facility with the corresponding room. On the top, you'll see the constituents: lighting, irrigation, dehumidification, HVAC, and mechanical aeration. What we have done in this exercise, just to illustrate the point, is to increase the lighting power consumption by 10%. And this then demonstrates the non-linear effect that that increase has across the board. Essentially, what it comes down to, if you look at the total kilowatt hours, the difference between 4,500 kilowatts and 3,800 kilowatt hours per day. What that means is that we have a non-linear increase in the energy spent as a result of lighting. That's very important to keep in mind. Now let's get to the income statements, the cost of goods sold comparison. It's very important to know what drives the cost factor when it comes to your production. In South Africa, we've got a unique phenomena of rolling blackouts, so people have diesel generators, battery supplementation, and solar PV arrays. But here you can see the difference in your operating margin, which is the yellow bar here in the bottom, as well as your cost per gram analysis. Essentially, it does not make sense to go with a diesel supplemented solution. You have 7% less operating margin, and your cost per gram is much, much more. Naturally, this comparison does not include solar PV, but the more solar PV you invest in, the larger your capex, but the larger your operating margin. So the goal is to find the best balance between these points. How does this translate to the balance sheet? Well, any ROI is a function of your capex, your operating margin, and your capex. If you look at your capex breakdown, again, more than half of it should be in your cultivation. And if you look at the internal cost breakdown of your cultivation, again, you will find the following pattern of that interdependency. Your lighting, air handling, HEPA filtration, ducting, dampers, grills, humidification, dehumidification, mechanical aeration make up, again, close to 90% of the capex components in your cultivation section. So what are the key takeaways here? The influence on the operating margin and net profit, the income statement. We see a very strong interdependency with regards to your technology selection framework. We see that the influence on your power consumption is non-linear. And we see that these factors have the greatest bearing on your profit margin. Again, on the capex side, we see that it's got the greatest bearing on your energy solution, whatever solution you decide to facilitate some reduction in your power consumption, which drives your costs. And the technology selection framework have some of the greatest capex contributions. So when you look at something which is essentially the optimization of your biological process on which you build your business, it's already very important. When you now take into consideration that it's got the greatest bearing on your operating margin and on your capex, you see that it is absolutely the most important consideration for any entity who concerns themselves with cultivation and production. In short, your technology selection framework underpins your commercial success. So if you're ever interested in getting that right, you're welcome to speak to us. This is our contact information. We are AgriSmart Engineering. We're proudly South African, and we thank you for your time.